segment 3 of in situ permeable reactive barriers. We're talking about some examples of permeable reactive barriers applied to mixed plumes or petroleum hydrocarbon plumes. In this segment, we'll talk about a funnel and gate system that was designed to treat a naphthalene plume in using a biological system where we were adding nitrate as an electron acceptor. The study was conducted at Canada Forces Base Borden in the Borden aquifer. You may remember we've discussed a coal tar creosote plume there previously. The plume is shown on day 1357 from the source extending perhaps 50 meters down gradient. The plume underlies the sand pit at Borden. The white features are wells, multi-level wells with 14 points to sample these plumes as they evolve. And we had placed a coal tar creosote source, and we're watching that plume. The plume was getting a bit long, and so it provided a good opportunity to try a funnel and gate cutoff system. We had made the source, as you may remember, of coal tar creosote by putting sheet piling in the ground in a box. We then dewatered the Borden sand, excavated the sand. We replaced at least part of that sand with a coarser sand into which we had added coal tar creosote at less than residual concentration. We then filled the hole up with that sand and then Borden sand, removed the sheet piling, and the lateral flow system was reestablished, creating the plume you see on the right. So, we decided it was a good place to put a funnel and gate, and that's what we did. This time, in about 1997, hanging funnel and gates were unusual. In fact, I don't think there were any. Normally, the funnel and gate systems were keyed into the lower aquitard. The idea was to stop plumes from being able to dive under the treatment system. We decided that that was potentially a waste of resources, building a deeper funnel and gate than was required. And we wanted to see if in a simple sand aquifer you could predict with confidence the behavior of the plume in and around the funnel and gate that would allow you to design hanging funnel and gates in other systems. Here's some pictures of the gate construction. This is sheet piling as the funnels, and we also use sheet piling to construct the gate. Again, we made a sheet piling box, we dewatered it, we removed the sand, and put the gate in place. The gate's a very special gate. It's a cassette gate. It's a frame that is screened front and back with permeable stainless steel so that groundwater can move through it. Into that frame we put cassettes. These were removable cartridges in which we had the treatment system. The cartridges we chose were shown here as briquettes. They're blocks of concrete, special concrete, manufactured with some sodium nitrate in the formulation. Bob Borden from the US has shown that you can design these briquettes in a certain way with this addition that will allow the briquette to release nitrate slowly over a considerable period of time. Our colleagues at the Royal Military College in Kingston, Ontario, Canada, were in charge of this gate design. They evaluated the release rates in labs and chose the size of the briquette you see there. If we wanted a faster release, we'd simply make a smaller briquette with a larger surface area to volume ratio. On the right, we have a picture of the cassette gate system. The 4 cassettes are shown. The cassettes are linked to the funnel system with bentonite seals. And the gate is open front and back to allow groundwater to go through. Here's a close-up of the cassette with the nitrate briquettes in it, and you can see the sampling tubes for multi-level monitoring as always. Here's a plan view of the setup, the funnels, and the gate with its 4 cassettes, and a bentonite barrier tying the cassettes to the funnels. Again, just to illustrate the hanging nature of the funnel and gate, there's considerable end aquifer below. Well, a major interest on our part was designing the plume capture. Could we actually predict how much of the plume we would capture? Well, the capture depends in part on the relative permeability of the cassette or the gate to that of the aquifer. So you can see here that if the cassette and the aquifer have about the same permeability, we get a certain interesting feature for the capture zone. Water inside that zone goes into the gate. Water outside that line goes around the gate. If we make the gate more permeable than the aquifer, we can increase the capture zone, but only slightly. In fact, we had designed for a more permeable cassette, and subsequently we had actually measured the permeability of the cassette, and it was even better than we had designed. So we have a fairly good idea of the capture zone. The interesting feature of the capture zone are these curved bottoms, and that's again because we have a hanging system. Water outside of that area is likely to go down as well as to the side as it goes around the funnel. A number of monitoring wells existed in rows up gradient of the funnel and gate system. We looked particularly at row 13 to design where we should put the system. We installed some additional monitoring along row FF to see where the plumes were going if they did go around the gate. We'll show you that in a moment. So here's a picture of the results at row 13 in red, the contour of the naphthalene plume. You can see the naphthalene plume is centered on piezometer 13.2. Unfortunately, I was the one charged with locating the funnel and gate, and I mixed up piezometer 13.2 and 13.3, and I ended up centering the gate on well 13.3 instead of 13.2. But as any good researcher, I try to make up for these mistakes, derive some value from it. What you can see here is we now are sure that a large portion of the plume is going to escape the gate treatment. Question then for us at Waterloo was, could we predict where that would go? If we could predict where that would go, it would suggest our modeling is somewhat robust and perhaps provides a reasonable understanding of the hydraulics around a funnel and gate. So sure enough, we modeled and we had installed some additional piezometers to see where the plume went, and it did go around the funnel and gate, mainly to the left side and a little bit down. And that turned out to be essentially where the model had predicted we would find the plume going around the gate. Much of the plume went into the gate, however, and so we had some opportunity to treat the naphthalene contamination. So what lessons did we learn? Well, residence time in the gate is sensitive to the predicted gate hydraulic conductivity. Certainly the gate has to be at least as conductive as the aquifer, and the more conductive it is, the larger the capture zone. Visual mod flow with good understanding of the local geology provided a robust prediction of plume capture. We had noticed this point before, but it may require quite a while for the construction activities to cease creating uncertainties and variations in the hydraulic flow system. So in this case, it took us at least 3 months before the hydraulics seemed to have stabilized. That's a long time to wait before you can evaluate the success of your system. The capture performance was predictable, at least in this simple aquifer, with simple numerical modeling. What about the naphthalene treatment? That was the responsibility of our colleagues at the Royal Military College. They did the design and led the monitoring of that. We had predicted the nitrate would release for something like 12 to 16 months. We monitored it only for 4 months, but it was releasing as we had expected. We'd stopped monitoring because winter had arrived. So we think that nitrate briquettes were a very good, interesting way of adding nitrate in a fairly passive, semi-passive way. Cassettes would allow you to recharge the nitrate briquettes every year if you needed in order to keep up the nitrate application. The nitrifiers became active right in the very first cassette with the briquettes. In fact, they seem to colonize the surface of the briquettes. Somewhat logical, I guess. That's the optimal position where the nitrate is at highest concentration and the naphthalene is present. All reactions, all denitrification and naphthalene degradation occurred within the initial cassette. The downgradient cassettes were there to slow down the migration of naphthalene and allow additional sites for the bacteria to colonize and allow the naphthalene to be treated in the gate if it took a little bit longer than we had anticipated. Turned out that was unnecessary, but not an unreasonable design feature. My story is the gate actually scared the naphthalene plume. We did measure that naphthalene was going into the gate and was disappearing before it got into the second cassette, But in fact, I think most of the naphthalene degraded before it got in the gate because it was scared. Why do I say that? Well, you may remember we had mapped the naphthalene plume at a number of times before this experiment and after. The naphthalene plume grew until day 1357 when we put in the funnel and gate. Subsequently, the plume retreated. In fact, we were measuring concentration reductions of naphthalene of about 50% going into the gate during the 3 or 4 months we were monitoring. So the success of the treatment was not only due to the gate, it was also due to natural attenuation processes in the plume. We have a few more cases that we want to expose you to, and we'll do that in the next segment. Thanks for now. Goodbye.